All right, so we're going to try this video again since the first upload, the audio cut out. So we're going to see if we can do this the second time. Okay, so on this kinematics review, on a distance versus time graph, a straight horizontal line indicates what type of motion. Okay, so we have a position versus time graph. Okay, so that's going back to unit 1. So if I had a horizontal line, something like this, okay, and then what would a straight diagonal line look like in the positive direction? So that means we're going to go up here. Okay, so we're going to label this A and label this B. So if I was asking what's going on at part A, I would say that would be no motion because your position is not changing. Okay, now part B is you have a nice straight constant diagonal line. Okay, so that means you start moving in the positive direction and it's going to be a constant velocity because your slope is not changing. Okay, so that is position versus time. So the big thing there is a flat line on position versus time graph means you are not moving. And now we're going to go take a look at a velocity versus time graph where we're basically just going to draw the same thing. But now we're going to change up that y-axis and it's going to be a v versus t graph. So I'm going to draw that horizontal line and then I'm going to go up. So on a v versus t graph, if I have part A and part B, part A now is a constant velocity forward. Two reasons why. So one is your velocity is not changing. Okay, so if I say this was like 5 meters per second right there, that just means I'm constantly going 5. It doesn't mean I'm not moving. It just means I'm constantly going 5 meters per second. Okay, and then the fact that it's forward means you're above the x-axis. That's how you know you're going forward on a v versus t graph, which we'll do more later. And then part B is my velocity starts increasing. I'm going away from that 0 at the x-axis. So that would be speeding up forward or accelerating forward, either one. So as long as you know that your velocity is increasing in the forward direction. And we'll do a lot more graph practice here in a minute. So a runner is jogging 6 meters per second, so that's velocity. Okay, 85 meters, that's displacement. Okay, what is the displacement? Now that should have been that was a typo. It should have said what is the time of the jogger. So if you've been trying to work that one out and you're like, what the heck's going on? That's why. So I've got V, I've got D, and I'm looking for T. So all I got to do is V equals D over T. Okay, so my velocity is 6. 85 meters is going to go on top. Time goes on bottom. So remember, anytime you're looking for a variable, you can switch those two if a variable's on bottom. So you're going to get a time of 14.17 seconds. Now, in this unit, I know we've been going over Daffy T. So if you're setting up every single problems like Daffy T, you can do that if you want to. Like if you tried on this one. So let's just say you did. Okay, distance would be 85 meters. Okay, so the runner's jogging 6 meters per second. So you don't even know if that's initial or final. Okay, so you wouldn't even be able to put it anywhere. So let's just say you even picked one. So let's just say it's initial. Okay, what is the time? So you're looking for time. So that means you don't have A or VF, so you would see that there's not enough there. So that's a hint, is if you're used to doing Daffy T and there's not enough there to do it, that means you don't need to do Daffy T. That means you just got to use one of your more basic equations like V equals D over T. Number 4, a bicycle travels 12 kilometers, so that's displacement. Okay, for 40 minutes, that's time. What is the velocity? So we're looking for V. Now, usually our velocities are in meters per second or kilometers per hour. So instead of converting both time and displacement to meters per second, I'm just going to fix this 40 minutes and change it into hours. Okay, so all you got to do is take that 40 and divide it by 60, and that'll give you 0.67 hours. Okay, so now if I'm looking for velocity equals D over T, so 12 over my time, 0.67 hours. So 12 divided by 0.67 gives me 17.91 kilometers per hour. 5, compare and contrast the equations for velocity and acceleration. So velocity equation is V equals D over T, and acceleration is change in V over T. Okay, so first, they both use time. So they both need that time, so that's something they have in common. Now when you look at velocity, velocity is change in displacement or your position. Okay, so if you're covering ground per time, like if you're driving your car and you got 60 miles per hour, that's how many miles you're covering every hour. Okay, acceleration though Acceleration is your change in velocity. So now all of a sudden it's how quickly are you changing your speed or your velocity. So like if you're in a car and you step on the gas, now you're accelerating. Okay, so that means your velocity is changing. So that is the big difference, is velocity is change in displacement or where you are. And acceleration is how quickly are you changing your velocity, either speeding up or slowing down. 6, a pitcher takes 0.010 seconds, so that's time, to throw a baseball which leaves his hand with a velocity of 3 meters per second. So we know that's velocity. Okay, what is the acceleration? So A is your question mark. Okay, assume the ball starts from rest. All right, so that just told me my VI is going to be 0. That means the 3 was my VF. Now, there's 2 ways you can totally do this problem. You can do Daffy T way. I'll show you both ways just in case. So Daffy T, so A, we don't know. VF is 3, VI is 0, and time is 0.010. Okay, and I'll do units for this one. So V final will be meters per second. V initial would be 0 meters per second. Time would be seconds. A is going to be meters per second squared. And distance is going to be meters, but we don't care about it, but its units would be meters. So I'm just going to go over those units right there real quick, just so you can see what the units would be. But during this video, I'm going to try to save time and not write those units every single time. So if you need to go back and look at units, you can rewind it or go look in your notes. Okay, we're going to try to save some time. Okay, so that means we don't care about distance. So you'd use equation number 1 on your equation sheet. So VF equals VI plus AT. So VF is 3, VI is 0, plus AT. So A we don't know, time is 0.010. So what I would do is I would divide both sides by that 0.010. So 3 divided by that, it's going to give me an acceleration of 300 meters per second squared. So there's your answer there. Now you could have also done A equals change in V over T. Okay, so A equals your final minus initial, so 3 minus 0, over T, 0.010. So it would have been the same thing, so either way would have been right. There was just a couple ways you could have gone about that. So A would still be 300 meters per second squared. So there's different ways you can do it sometimes. Usually Daffy T is the right way to go, but sometimes there's different ways to do it. 7, how long does a car with an acceleration of 2 meters per second squared take to go from 10 meters per second to 30 meters per second? So again, you could do this again both ways. I'm just going to stick with Daffy T on this one, but if you do it the other way, that's totally fine. Okay, 10 meters per second would be my initial. 30 is going to be my final. I have an acceleration of 2.0. How long does it take? So you're looking for time. That means we did not care about distance. So that is going to be where I draw my line. So I'm going to go back to using that same equation, VF equals VI plus AT. So VF is 30, VI is 10, plus A, which is 2.0 times T. So algebraically what I would do is I would take that 10 over to the other side. That's going to make it 20 over here now since we minus 10, equals 2.0 T. So divide both sides by 2, and you get a time of 10 seconds. 8, a car undergoes a constant acceleration of 6.0 meters per second squared. So let's just go ahead and start setting up our Daffy T. A is going to be 6.0. Starting from rest, so VI is going to be 0. How far does it travel in the first second? So you're looking for distance, and I gave you time was 1 second. That means we did not care about VF. So we're going to do the D equals VIT plus 1/2 AT squared. So D I don't know, leave it as D. VI is 0, so we can go ahead and get rid of that whole VIT. That'll save us some time. Equals 1/2, A is 6, and then time is 1, and that's squared. So all you gotta do is just solve that out, and you're gonna get a distance of 3 meters. Okay, number 9, an airplane requires 20 seconds and 400 meters of runway to become airborne. So let's go ahead and set up our Daffy T. Okay, so I have 400 meters of runway. Time is 20 seconds. Starting from rest, so V initial is going to be 0. Okay, what is the velocity when it leaves the ground? So that means you're looking for VF. And that means we did not care about acceleration. So we're going to use equation number 2. So D equals VI plus VF all over 2 times T. So I'm going to start plugging in. So 400 equals VI, so 0 plus VF, which we don't know, over 2 times 20. Okay, so first thing I'm going to do is I need to get rid of that 20, okay, so I can start working to get VF by itself. So I'm going to divide both sides by 20. That's going to give me 20 equals VF over 2. Now, if I want to get rid of that 2 on the bottom, I would multiply both sides by 2, and you're going to get a final velocity of 40 meters per second. 10, a car has an initial velocity of 15 meters per second. Okay, so let's go ahead and set up our Daffy T. So initial was 15 meters per second. Acceleration of 1.0 meters per second squared. Okay, so that's going to be A equals 1.0. In the first 10 seconds, so T is 10. After its acceleration begins, how far does it go? So it's looking for distance. Means we did not care about velocity. Now, one thing I want to address real quick about acceleration is I know that when we introduced gravity, where all of a sudden now gravity is negative 9.8, and sometimes it can get stuck in your head that it's always that, but that's only when we're in free fall. That's if I throw something in the air, if I drop something down. Okay, if I'm talking about a car driving on the road, it's not falling or being thrown in the air, so I'm not going to use gravity as my acceleration. Okay, it's only during free fall questions that you can just automatically know that's negative 9.8. So just be careful of that. Just don't put gravity in every single problem if it's not falling or being thrown. All right, so what we're going to do is we're going to use the third equation. So D equals VIT plus 1/2 AT squared. So D we don't know. VI is 15. Time is 10 plus 1/2 A is 1. And T is 10 and that's squared. Please just make sure you square the 10 only, not the whole thing. Okay, so all you gotta do is solve for the math on that one, and you're gonna get 200 meters. Number 11, this is basically the exact same problem, but we're just switching up our negatives now. We're switching our acceleration to negative. So D is still your question mark. A is negative 1.0. VF we still don't care about. VI is still 15. And then time is still 10. Okay, so all we're doing is we're showing what happens when we have a negative acceleration, because that means we're slowing down now. Okay, so we're going to use the exact same equation. I'm not going to write it again for this one, but I'll fill in the blanks. So D equals 15 times 10 plus 1/2. Now you get negative 1 instead of 1, and then still 10 squared. So this is where you got to be careful, because that negative can make a really big difference between 200 meters, and now if you solve this, you're going to get a distance of 100 meters. So you can see how just missing a sign like that can really create a big difference. 12, how far does the car in question 11 travel before coming to a stop? Okay, so we want to know about, we're coming to a stop, so that's a key hint right there. So we're going to do Daffy T. Coming to a stop means your final velocity is going to be 0 now. Okay, so we're still going to use the things they gave us. So we still have an initial velocity of 15. I still have an acceleration of negative 1.0. Okay, now here's the kicker is you cannot use that 10 in number 11, because that just wanted to know how far did it go when it began to decelerate. It didn't say that it stopped. That's just how far when it began to slow down. So we can't assume that 10 seconds is the time it took to stop. So in this case, we don't know time, and we're looking for how far it goes. So D is our question mark. So we're going to use equation number 5. So VF squared equals VI squared plus 2AD. Okay, so VF, 0. VI is going to be 15. That's squared plus 2 times negative 9. So I'm sorry, I got into that free fall mode. Negative 1.0. Just saw that negative and went gravity. And then distance, we don't know. Okay, so what I would do if I was doing this algebraically, I would take this 15 squared and move it to the other side. So that'd be negative 225 equals negative 2D. Okay, so all I got to do is divide both sides by negative 2. And you're going to get a distance of 112.5 meters. 13, a wheel falls from an airplane which is flying horizontally at altitude of 490 meters. Now this one's I've been seeing more confusion on this one, is you have a plane that's flying horizontally and we're dropping something from it. So I'm seeing a lot of trouble with your initial velocity on this one, and we'll go over it on this. So I have an altitude of 490 meters. Now, a wheel is going to be falling from that plane. So if it's falling that distance, that's technically a negative 490 meters. Okay, we're not going up to it. Okay, we're falling from the height of the plane, which is 490. So it's technically negative 490 from where it was. Now, since it's falling, now we get to use gravity. So negative 9.8 is going to be your acceleration. Now, your initial velocity is going to be 0. Okay, this is where the confusion is happening, is because yes, the plane is moving, but the plane's not falling down. Okay, what it's doing is it's flying horizontally, and then a wheel falls off and starts going down. So your initial vertical velocity is 0 because it's not falling yet, and then it starts to fall. Okay, so just be careful with that. So I want to know which is flying, and how many seconds before it hits the ground. So you're looking for time. That means we did not care about VF. So we're going to do D equals VIT plus 1/2 AT squared. So D is negative 490. We can go ahead and cross out the VIT since VI is 0. Equals 1/2 A, which is negative 9.8, and T squared. So 1/2 times negative 9.8 is negative 4.9. Okay, I would divide both sides by negative 4.9. Okay, that would give you 100 equals T squared. Now you got to get rid of that squared. You can't leave it as T squared. So what you would do is you'd square root both sides to get rid of that squared. So square root of 100 would be 10. So T equals 10 seconds. Now the reason why that negative 490 was important on this one is because if you didn't put negative 490, now all of a sudden you're going to try to take the square root of a negative number, and your calculator won't do it. It'll just pull up an error symbol. Okay, so just watch out. So for anything that's going down, like if you're falling down, the distance is going to be negative, the velocity is going to be negative, so anything going down is going to be negative. That's why gravity is always negative, because even if you're going up in the air, it's always still pulling you down. So that's the direction that acceleration is going. 14, a stone is dropped from a cliff after it's fallen 30 meters. What is the final velocity? So we're going to set up our Daffy T. Now it's falling. So negative 9.8 is going to be your acceleration. It's falling 30 meters, so that's negative 30 meters. Okay, what is its final velocity? And when you dropped it, it didn't have any velocity first, so that's 0. And T we don't care about. Now, of questions I've seen on this one is when it hits the ground, it has a velocity of 0. Well, technically, once it hits the ground and comes to a rest eventually, it will have a velocity of 0. That's not what I'm asking. I'm asking is, what is the velocity when it hits the ground? So I want to know how fast is it going when it hits the ground. So we're going to use equation number 5. So VF squared equals VI squared plus 2AD. So VF we don't know, so we're going to leave that as VF squared. VI is 0, so we don't have to worry about that, so we can get rid of that. Equals 2 times negative 9.8 times D, which is negative 30. Okay, so VF squared equals 588. Square root both sides, and you get a final velocity of 24.25 meters per second. And I'm going to go ahead and say that's going down. Okay, you could draw an arrow to explain which way is it going. You could say 24.25 meters per second and then draw an arrow going down. I'm just telling you that that's the velocity when it's going down, or when it hits the ground, that it's negative. All right, number 15, a ball is thrown vertically upwards at 25 meters per second. Okay, continues to rise for approximately how many seconds? So we're going to set up our Daffy T. Just be careful when you're setting up Daffy T. You need to keep it in that order. I've seen some that are kind of jumbling it around. That's fine, but you got to be careful if you're using the equation sheet that I give you that has all those equations listed in a specific order, and then you're jumbling things around, okay, that can kind of lead to some issues with you using the wrong equation. So just be careful if you're doing that. So thrown vertically upward. So I get some confusion on this one too, is when I'm throwing something up in the air, it has to have an initial velocity to even leave my hand. Okay, so that 25 meters per second is my initial velocity. Okay, now if I'm throwing it up in the air, eventually it's got to stop. So at the top, your final velocity's got to be 0. Now, if I'm throwing something or anything's falling, gravity is going to be present, so A is negative 9.8. And I want to know how long was it basically in the air for, so we're looking for time. That means I did not care about distance. So we're going to use equation 1, so VF equals VI plus AT. So VF is going to be 0. VI is 25 plus A, that's negative 9.8 times T. So I'd move that 25 over, it becomes negative 25 equals negative 9.8 T. So divide both sides by negative 9.8 and you get 2.55 seconds. 16, in question 15, how much time will pass before the ball strikes the ground? Okay, so there's two ways you can kind of answer this. One is if it takes 2.55 seconds to go up, okay, and there's no wind resistance, nothing affecting its path, it's going to do is it's going to take 2.55 seconds to go down. So you could answer it that way, where that's how long it took to fall from the top. Or if I ask something like how long was it in the air, all you got to do is take that 2.55 plus 2.55, and that means it's in the air total for 5.1 seconds. Okay, so two different ways you can kind of answer that. 17, a ball is thrown downward at 5 meters per second. So this is where we got to be careful. Okay, because I've seen some confusion on this one as well. If I'm throwing something down, that means my velocity is negative. Okay, and again, what is the velocity when it hits the ground? So that means that 5 meters per second was my initial. Okay, so it had to leave I threw it downwards. I didn't just drop it. I threw it downwards at 5 meters per second, so that makes it negative 5. And I want to know what is the velocity when it hits the ground, so that means you're looking for VF. Gravity is present, so negative 9.8 is your acceleration. And since I'm falling from a 10-meter height, or I'm going downwards 10 meters, that distance is technically negative 10. So that means time we did not care about. So we're going to use VF squared equals VI squared plus 2AD. So VF squared we don't know. VI is negative 5 squared plus 2 times negative 9.8 times 10. Negative 10. Okay, so I would get that answer. So VF squared equals 221. And then square root both sides, and you get a final velocity of 14.87 meters per second down. Okay. All right, use the graph to the right to answer question 18 through 20. This is a position versus time graph, so be careful with this. This is going back to kind of unit 1. Okay, which section indicates the object is not moving? That's when you're looking for a flat line. Okay, that means you're not changing your position, so that means from basically 1 to 3 seconds, you're staying at 10 meters. So you didn't move. Okay, so that would be B. Which section indicates the object's moving towards the original position? Well, if I started at 0, I'm looking for the time where it's going back towards 0, so that would be C. And then 20, which section indicates the object is moving forward? That means going away from 0. That's going to be A. Okay. All right, so I know this graph doesn't look the best. Okay, we'll do our best what we got. So this is a V versus T graph. So we're switching things up a little bit, so be careful with this. So if I ask anything for velocity, velocity is always just going to be your y-axis. Okay, so if I ask for change in velocity, all you got to do is look for the change in y-axis. If I ask you what is the velocity, just look at the y-axis. If I ask for anything about acceleration, acceleration equals slope. Okay, so if I ask anything about acceleration, you need to find the slope. Okay, so what I'm going to do is real quick, I'm going to go through what type of motion is going on in this graph before I even answer these questions, because that's where I usually see more issues. So this 0 to 2. Okay, so 0 to 2, so like right here, and I can use I wonder if I can go bigger than that. Maybe not. All right, so what I'm going to do is from 0 to 2, we're not moving because your velocity is 0. Okay, that 0 line, the x-axis is 0. Okay, then what happens is you start going down. Okay, so that means you are speeding up because you are going away from 0. Now, anything above the x-axis is going forward. Anything below the x-axis is going backward. That means you're going in a negative direction. So what this would be is this would be speeding up backwards. Then, at 5 seconds, I start going back towards 0. I'm not going forward yet. Okay, I'm still below the x-axis. It just means I'm slowing down. I'm going back towards 0, that x-axis line. So this would be slowing down backwards. So at 6 seconds, I stop. Okay, I hit 0. Now, once I go through that x-axis, that means I change directions. So that means I'm going forward now. And now I'm going away from 0. And now I'm above the x-axis, so you're going forward. So that's speeding up forward. Then I'm going constant velocity forward since I'm above the x-axis, so CVF. Then what happens is I start slowing down. I didn't change directions yet. I'm just slowing down, still going forward. Okay, then I stop, and then I start going down. Okay, so now I'm going backwards again, so because I went through the x-axis, and I'm going away from 0, so that's speeding up backwards. And then I start going back towards the x-axis, so I'm slowing down backwards. And then I'm going constant backwards, so constant velocity backwards. And then I start slowing down again, so that would be slowing down backwards. And then it looks like I stop again at 19 seconds. Okay, so that's just kind of the gist of what type of motion is going on. So let's actually go to the problems now. So what is the velocity object at 2 seconds? That means just look at the y. Where are you at 2 seconds? So at 2 seconds, I'm at 0 meters per second. Okay, there's nothing there. All you gotta do is just look at the y-axis. At 10 seconds, right there, look to the left, and you're at 2 meters per second. 14 seconds, look to the left, you're at -6 meters per second. Okay, 22 is what is your change in velocity? So change in velocity is what was your final velocity minus what was your initial velocity. So from 5 to 7 seconds, okay, so at 7 seconds, that's your final, so V final. 5 would be your V initial. So my final, so 7 seconds, if you look at 7 seconds and you look to the left, you're at 2 meters per second. Minus, where were you at 5 seconds? You're at -3, so minus a -3. Be careful with your math here. That's going to come out to be 5 meters per second. 7 to 12 seconds, so at 7, okay, that would be your initial. 12 would be your final. So at 12 seconds, where are you? Look to the left, you're at 2 meters per second. Minus, where are you at 7 seconds? You're also at 2 meters per second. That's going to be a change in velocity of 0 meters per second. It should make sense. You didn't change velocity. C, 12 to 14 seconds. So at 14 seconds, where are you? Okay, so at 14 seconds, you're at -6. Minus, where are you at 12 seconds? So at 12 seconds, you're at 2. So -6 minus 2, that gives you -8 meters per second. 23, what is the acceleration at 4 seconds? So remember, acceleration is slope. Okay, so that is going to be your V final minus your V initial, or Y2 minus Y1, over your time. Okay, or X2 minus X1. Okay, so that's what you need to look for. Is at 4 seconds, what I'm going to do is, yes, at 4 seconds, you are on this line. So I'm going to change colors. You're right there. Okay, if you're on a line, all you got to do is find the slope of that line. So I would use these two endpoints right here to use my slope. So my slope, my point right here would be 5, -3. And my first point would be 2, 0. That's all you got to do is just find the slope of that line. So you do your Y2 minus Y1, so -3 minus 0 over your time, 5 minus 2. Be careful with this. Don't use the 4 seconds. Okay, you want to know what is your change in time of that line. Okay, not what it is specifically at that 4 seconds. So -3 divided by 3 is going to give me -1 meters per second squared. So at 9 seconds, this one's easy. Okay, you have a flat line. That doesn't mean you're not moving. Okay, it just means you have a constant velocity of 2. And if you're not changing velocity, you're not accelerating. So your acceleration would be 0 meters per second squared. And then at 15 seconds, so at 15 seconds, you're right here. So all you need is your endpoints. So your endpoints right here would be 14, -6. And my endpoint here would be 16, -2. So Y2 minus Y1. Okay, so -2 minus a -6 over X2 minus X1, so 16 minus 14. And you're going to get 2 meters per second squared. When does the object change directions? That's when you cross the x-axis. That's when you go from positive to negative or negative to positive. That's going to happen 2 times. That's going to happen at 6 seconds and 12.5 seconds. So again, that's crossing the x-axis. That's when it happens. When is the object moving in the positive direction? Anytime you're above the x-axis. Okay, so anytime you're going positive, you're looking for above the x-axis. So that would be from 6 to 12.5 seconds. Negative would be anytime you're below it. It can be multiple different times, just anytime you're below it. Okay, so you're actually going negative from 2 to 6 seconds, and from 12.5 to 19 seconds. Okay, so you can have multiples. When does it have constant velocity? Now that is when you have constant velocity, a flat line that's not on zero. Okay, if you're on zero, that means you're not moving at all. Okay, so look for a flat line that's not on zero. Okay, and that's 7 to 12 seconds and 16 to 18 seconds. Here at 27, what time is the car stopped? Okay, so pay attention to your velocity at 0. Okay, it's not stopped in the beginning. It's actually the fastest it's going is right there at the beginning. Okay, and then it starts slowing down. So at 12 seconds, that's when it stops. Okay, the object is slowing down during which time interval? So anytime you're going towards 0. So if you're going towards 0 like this first part, that's slowing down. So from 0 to 2 and from 10 to 12. Okay, and I think I just found a mistake on my key. That should be 10 to 12, not 9 to 12. I think I was just looking at it from the side. Okay, 29, the acceleration from the object from 2 to 4 seconds was, so 2 to 4. Well, I have no slope, so that means there's 0 acceleration going on. And then 30, the acceleration of the object at 0.5 seconds. So at 0.5 seconds, it's like right, I'll use a different color now. 0.5 seconds, you're like right here. Okay, all you gotta do is find the slope of that line. So all you need to do is pick the endpoints. So my endpoints would be 0, 10, and then I would have 2, 1. Okay, so I would do 1 minus 10, y2 minus y1, over x2 minus x1, so 2 minus 0, which would give you negative 4.5 meters per second squared. 31, the change in velocity from 2 to 12 seconds. Okay, so I just want to know, what is my change in y? Okay, so that is going to be your v final minus your v initial. So at 12 seconds, where are you? Well, you're at 0. Minus, where are you at 2 seconds? At 2 seconds, you're at 1. So 0 minus 1 gives you negative 1 meters per second. 32, the position versus time graph would be curved for which of the intervals? So anytime there's something curved, like on a graph, that was when you were either speeding up or you were slowing down. Okay, so you're looking for when are you speeding up and when are you slowing down? Okay, so from 0 to 2, you're slowing down. So there's 1. Then from 4 to 6, you're speeding up. So there'd be another curved line. And then from 10 to 12, you would be slowing back down again. 33, when did the object start to turn around towards the opposite, towards the starting position? Be careful. Okay, I'm going to put this in red. This does not mean you turned around. That just means you're slowing down. We have no idea where you're actually at. We're just looking at your velocity. You're slowing down. So in this case, it never happens because in order for it to happen, it would have to keep going through the x-axis past 12 seconds. We don't know if it did or not. Okay, so that means it never happened since it did not cross the x-axis. Which time interval shows the object moving at uniform velocity? That just means constant. So you're just looking for flat lines. So that'd be from 2 to 4 and 6 to 10. All right, almost done. So describe what's going on here. So A is going to be a constant velocity forward. So again, remember, anything above the x-axis is forward. Anything below is backwards. Okay, flat line doesn't mean you're not moving. Okay, it means you're just going constant velocity. So that's the only thing that's happening in A. It's just constant velocity forward. B, if you look at B, what's happening is you're below the x-axis. So that means you're going backwards, and you're also approaching this 0 line. You're approaching the x-axis. So that means you're slowing down backwards. Then you stop because you hit the x-axis, so you stopped. You went through it, so that means you changed directions. And now you're going away from 0, and you're above the x-axis, so now you're speeding up forward. That was it. C is the opposite. Okay, so if you look, C is going towards the x-axis, but you're above the x-axis, so you're slowing down forward. Then it stops, and it changed directions because it went through it. And now if you look, it's starting to go, it's below the x-axis now, and it's going away from 0, so this is speeding up backwards. What's happening D? So D is you start at the negative position, you're going away from 0, so you're speeding up backwards. And then it looks like you start flatlining, so that means you're just going a constant velocity backwards after that point. Then E never goes anywhere. It stays below the x-axis, so that means it is just a constant velocity backwards. All right, so hopefully the audio sticks through on this one, and that helped.